Hello students, in this session we are going to discuss indefinite integration. So, we define integration as a reverse process of differentiation. What does it mean? It means that, we say that derivative of sin x with respect to x is cos x, right? So, reverse process means antiderivative of cos x is sin x, right? So we call antiderivative as integral, right? So we say that integral of cos x is sin x, and the symbol for integration is cos x with respect to x. That means integral of cos x with respect to x, right? And this value is equal to sin x plus some constant c, because for any constant we have its derivative 0. So if we differentiate this term with respect to x, then we will be getting cos x, right? So we define integration in that way. Now we can write in general, if derivative of fx is capital Fx, we say that integral of capital Fx dx is fx plus c. So this is called indefinite integration. Okay. Now we perform indefinite integration just by checking which is the antiderivative of this function. So we have some reverse formulas, like for sin x, this is integral fx. Okay. It is minus cos x. For cos x, it is sin x. For sec square x, it is tan x. For cosec square x, it is minus cot x. For x to the power n, it is x to the power n plus 1 upon n plus 1, where x is not equal to, where n is not equal to minus 1. 1 upon x log x base e, and all have a constant plus c, here also plus c, here also plus c. Fx, integral of fx e to the power x plus c. Okay. Sec x tan x, sec x, cosec x cot x minus cosec x, right? So these are some basic formula for indefinite integrations, which is nothing but the reverse of derivatives, right? Okay. Now there are some certain methods for performing integration. One of them is substitution. Okay. So let us have an example. Suppose we have to perform this integration. Then we have to see what substitution we have to do. Substitution means we have to change the variable, right? Here substitution means change of variable. From given variable, that is here, from x to another variable, from one to another, so that the function which we get after that, right, is based on these formulas, okay, this given chart which is our table, right? So we do like that. Suppose we have example in we have taken 1 plus log x whole square upon x. So if you check here, if we substitute, say we substitute a variable z as log x, then clearly dz upon dx we can write it as 1 upon x. So we can write dz as dx upon x. Okay. So this integral will transform to 1 upon z square dz, right? Because x dx upon x is dz. So this integral transform to 1 upon z square dz. If we evaluate this integral, then 1 upon z square is, again, say instead of taking z is equal to log x, if we take z is equal to log x plus 1, then dz upon dx will be 1 upon x only, and dz will be x only. So here, instead of writing 1 upon z, we can simply write z square dz. And see, this is of the form x to the power n. So we can write its integration as z to the power 2 plus 1 upon 2 plus 1 plus some constant, which is equal to z cube upon 3 plus some constant. Now what is z? Z is 1 plus log x. So it is log x cube by 3 plus c, right? So the value of integral I, let us name this integral as I. So I is 1 plus log x cube upon 3 plus c. So in this way we perform substitution. So there are various kind of substitution we will be seeing while solving the problems. Okay, there are trigonometrical substitutions. Okay, there are substitution for inverse trigonometric functions, and many more substitutions are there. So this is one of the powerful methods for performing integration by substitution. Okay, now next is integration using or by partial fraction. Okay, suppose we have to perform integral, we have to find the integral of one upon x plus 1 into x plus 3, say dx, this type of integral. Then here we will be first performing the partial fraction, that is we will be writing this as a upon x plus 1 plus b upon x plus 3, okay, and finding the constants a and b, so that we will be getting this form. So from here this value is this. So if we multiply the whole expression by x plus 1, so we will be getting a plus x plus 1 upon x plus 3b is equal to 1 upon x plus 3. Now substituting x is equal to minus 1, we will be getting a is equal to 1 upon 2, right? Similarly, multiplying the both expression, this and this, by x plus 3, we will be getting 1 upon x plus 1 is equal to a times x plus 3 by x plus 1 plus b. Now substituting x is equal to minus 3 in both LHS and RHS, we will be getting b is equal to minus half. So we can write 1 upon x plus 1 into x plus 3 as half upon x plus 1 plus minus half upon x plus 3. That is, we can write, taking half as a common, 1 upon x plus 1 minus 1 upon x plus 3. Okay. So if say we have an integral fx dx, integral of fx is say capital Fx plus b, then integral of f ax plus b dx must be capital F ax plus b upon a plus b. Okay, how is that? If we substitute, say let us substitute b as ax plus b, then we will be getting dt as a times dx, or we can write dx is equal to dt upon a. So this integral will become integral of ft dt upon a, which is equal to capital ft upon a plus b. Now what is t? Fax plus b upon a plus. So using this we can now evaluate the integral. So we have to evaluate the integral. I is 1 upon x plus 1 into x plus 3 dx, which we have by doing partial fraction we have transformed into the form half 1 upon x plus 1 minus 1 upon x plus 3 dx, right? So taking these two terms one by one, that is integral half dx upon x plus 1 minus integral half of integral dx upon x plus 3. So we know that integral of x will be log x base e plus c. So we can write integral of 1 upon x plus 1 as log 1 plus x base e plus c, right? Similarly, integral of 1 upon x plus 3 as log base e x plus 3 plus c, right? So we have the integration I as half ln x plus 1 minus half ln x plus 3. We take actually the modulus because these numbers cannot be negative inside the ln log. So we take modulus. So we have the property of mod as log a minus log b can be written as log a upon b, right? So we can write, taking half as a common, log x plus 1 upon x plus 3. So here this is the integral, value of integral, this. Okay. In this way we perform partial fraction. Now there is one more basic method which is called integration by parts. In this method, using this method, what we do, we transform a given integral into another integral, and we do perform the transformation such that the integral which we obtained after transformation will be easier to integrate, right? Suppose we have a function fx dx, okay, such that fx can be written as the product of two functions, right? Say that we have hx into gx is equal to fx, right? So we have to perform the integral of hx gx dx, right? In this one, first we define two functions, function 1 and function 2. First function and second function. For first function, we have to find its derivative, and for second function, we have to find its integral. So, the function for which we can easily find the function for which we can easily evaluate its integral. We will be taking that as second function, and the function for which and another left function we can take it as first function, right? So let us say here we have to gx can be easily integrable. Let us name gx easily integrable. So u is the first function, so we take u as hx and gx dx as dv. Let us take. So here we differentiate u with respect to x to get h dash x, and we differentiate v. So we integrate with respect to x. So this side we will be getting v is equal to, and since gx is easily integrable, we will be getting some integral value. Say we are getting gx plus g, right? We will not be considering this value, constant value. So we will be considering v as capital of gx. So we can write this integral as this is, then I is integration of u dv, right? So we can write this integral as uv minus integration of v du. So u is hx and v is gx, capital Gx into hx minus integration of v du. V is capital Gx and du is h dash x dx. So we have transformed the integral fx dx into another integral, which is this. So this integral must be easier to evaluate from this integral. Then only by parts will work, otherwise this will not work. For example, let us have an example. So we have, say, a very simpler function, fx is equal to x e to the power x. Okay, we have to find the integral of fx, x e to the power x dx. Now say, let us take first function as x, and second function we can write dv is equal to e to the power x dx. Now we have to integrate first function we have to differentiate, and second function we have to integrate. So let us do that. So we find du upon dx, which is equal to 1, and we will be integrating second function, that is dv is equal to e to the power x dx. So v is e to the power x, right? Now we write fx dx integral as integral u dv, because we have taken this as u and this as v dv. So we can write this as integral u dv. So integral u dv can be by parts. It can be written as uv minus integral of v du. Okay. So we have find u and v. U is x and v is e to the power x minus integral v du. V is e to the power x and du is equal to dx from here. So now this integral is easier to integrate, right? So we have integral x e to the power x minus e to the power x plus c, right? So x minus 1 e to the power x plus c is the required integral. Now let us take in opposite way. Let us interchange the function x e to the power x dx. So let us take u as e to the power x and dv as x dx. So let us find du upon dx. Du upon dx is also e to the power x, and if we find here v is x square upon 2, right? So by using by parts formula, integration of u dv can be written as uv minus integration of v du. So we have uv, u is e to the power x, v is x square upon 2 minus integral of v du, v is x square upon 2, and we can write du as e to the power x dx, e to the power x dx. So clearly, if you see here, this integral is transformed into this minus this integral. Okay, so it is more harder to evaluate this integral. The problem becomes more harder now by transformation. So this transformation we will not be performing. Okay, so we will be performing that transformation so that we can get easier function after transformation, so that the function after transformation is easier to evaluate. This function I am talking about, this function. So this is the method for using by parts. Okay, now there are some more types of formulas which I am going to write down. Okay, so we have suppose we have to perform this integral. So here we can substitute in place of x. Let us substitute x is equal to a tan theta. Then simply dx is dx upon d theta. We can write as a sec square theta d theta. Right? So dx can be written as a sec square theta. So dx can be written as a sec square theta theta. Now transforming this integral, we will be getting, in place of dx we are writing a sec square theta d theta, and in place of x we will be writing a tan x. So a square tan square theta plus a square under root. So this integral transform into a sec square theta d theta upon a square we can take outside, and 1 plus tan square theta. So we have a will be getting cancelled. So we have sec square theta d theta upon 1 plus tan square. 1 plus tan square theta is nothing but sec square theta. So sec square theta root under sec theta. Right? This integral. So this and this will be getting cancelled. Sec theta square will be getting cancelled, and we will be getting sec theta d theta. Now sec theta d theta, we can write sec theta as 1 upon cos theta. Okay, right? So the integral of sec theta, if you see further, cos theta can be written as 1 minus tan square theta by 2 upon 1 plus tan square theta by 2. So if we substitute this and one more by further substitution, you will be seeing that the integral value of sec theta d theta will be log of sec theta plus tan theta. So similarly we have integral cosec theta d theta as minus of log of mod of cosec theta plus this cosec theta plus cot theta plus c. Okay. Similarly, integration of tan theta d theta, we have log of sec theta plus c, and the integral of cot theta d theta will be minus of log of cosec theta plus. Now coming to our main formula, which is dx upon x square plus a square. Now we have the integral for sec theta, that is log of sec theta plus tan theta. Now the substitution for tan theta is x upon a. So we write sec theta as 1 plus tan square theta, right? So this can be written as log base e 1 plus x square upon a square under root plus tan theta is x upon a. Okay, mod plus g. If we want to separate one more constant term, then we will be transforming this value into something like log of base e x square plus a square under root plus x plus some another constant c1, where c1 is c plus it is actually c minus some constant, which is coming from the denominator a of this block. So let me write the formula. So we have integral of dx upon x square plus a square under root as log of x plus root under x square plus a square plus b. Similarly, we have integration for dx upon x square minus a square as log base is e x plus x square minus a square plus e, and we have integration for dx upon a square minus x square under root as sin inverse x upon a plus. Okay, we have integral of dx upon x square minus a square as 1 upon 2a log base e x minus a upon x plus a plus b mod. We have integral of dx upon x square plus a square as 1 upon a tan inverse x upon a plus. We have integral of x square plus a square dx as x by 2 x square plus a square under root plus a square by 2 log base e x plus x square plus a square plus. Similarly, we have integral for x square minus a square like this. Okay, so we have integral of a square minus x square dx as x by 2 a square minus x square plus a square by 2 sin inverse x upon a plus. So these are some ready-made formulas which you can prove also by using some substitution. Like here, in case of this, we have substituted x is equal to a tan theta. In this, we will be substituting x is equal to, here also if we substitute x is equal to, say, if we substitute x is equal to a cos theta, then also we are going to solve. Here also we substitute x is equal to a cos theta or sin theta, whatever. Okay, here partial fraction we are going to use. Here we will substitute x is equal to a tan theta again. Okay, here also we substitute x is equal to a tan theta again. Same is the case here, and here we will be substituting x is equal to a sin theta, right? Using this substitution, we are going to get the formulas which we will be using while solving the integration. Okay, let us have an example. evaluate the integral for 1 upon x to the power 4 plus 5x square plus 1 dx. So we have the integral I as dx upon x to the power 4 plus 5x square plus 1, which we can write as half integration of 1 plus x square upon x to the power 4 plus 5x square plus 1 dx minus integration of x square minus 1 upon x to the power 4 plus 5x square plus 1 dx. Right? Now this can be written as half integral of 1 plus 1 upon x square upon x square plus 1 upon x square plus 5 dx, and similarly this can be, another part can be written as half integral of 1 minus 1 upon x square upon x square plus 1 plus x square plus 5 dx. Now if we see, this is integral I1 and this is integral I2. Okay. For I1, if we substitute t is equal to x minus 1 upon x, okay, or we can write dt as x, we can write dt as 1 plus 1 upon x square dx. Similarly for I2, if we substitute t is equal to x plus 1 by x, then dt here will be 1 minus 1 upon x square dx. Okay, so the integral will reduce to I is equal to basically half of I1 minus I2. So half of integral will reduce to integral dt upon t square plus 7, okay, minus this integral will reduce to dt upon t square plus 3. Okay, so note that here t is different than this t because we have substituted some different quantities. So this integral 1 upon x square plus a square form, so we can write this as half into 1 by root 7 1 upon root 7 tan inverse t upon root 7, and for this we can write half of 1 upon root 3 tan inverse t upon root 3, right? So now substituting the value of our original variable, that is 1 upon 2 root 7 tan inverse, the value of t here is x minus 1 upon x minus 1 upon x upon root 3 minus half 1 upon 2 root 3, that is, this is now basically 1 upon 2 root 3 tan inverse, in this case t is x plus 1 by x, so x plus 1 by x upon root 3, x plus 1 by x upon root 3, right, plus, so this is the required integral. Okay, further you can simplify by taking tan inverse some x minus tan inverse b. Okay, but this is the required integral. So we use some given use this formula for finding the integral values also, and basically we try to make any integral in the form so that we can use the formulas, right? Okay, so these are all the method of integration we have seen. Now next we are going to solve some problems.